Okay. Okay, sir. So this is a second paper which I'm the only author for this. So it is a simulation of a four-leg inverter based APF means active power filter for PV based system with effective controller. Here we are using an effective controller. It is a general meaning. So we can use even PID controllers, neural fuzzy or etc. So this is also for a solar PV based system. So as we can see in the different type of distribution systems nowadays, they're going for an hybrid combination of a combination of an renewable energy sources which are coming into a picture of even government is also providing a subsidy for us. So we have gone for my main motto was electric vehicles and hybrid electric vehicles, sir, because from since 13 years I'm working on electric vehicles and hybrid electric vehicles. We have developed an electric vehicle in our college. So we want to integrate an electric vehicle to the smart grid. That was the theme. So for integration, we require an solar PV system, which is connected to the distribution system because we want to give an electric vehicle as at a distribution load. So when it is taking power from the grid to the vehicle, and when the vehicle is not operating mode, when it is a standalone mode, we want to give an reverse supply to the grid. It's a bidirectional process which is going on. So based on that, we are interfacing the three-phase four-wire distribution system for which we are checking the total harmonic distortion. Based on the total harmonic distortion of an inverter, we'll be connecting to the our source will be connecting to the vehicle. So the inverter which we have utilized here is it is a power converter to inject a power generated from renewable energy sources to the grid, and we have used a shunt active power filter to compensate the current unbalances, load current unbalances, and based on your linear load and non-linear load, balanced and unbalanced load. So in this study, we have considered an inverter and APF active power filter, and different types of loads are considered like linear load, non-linear load, balanced load, and unbalanced load. So we have considered all the four loads. So based on all the four loads, we could identify that non-linear and unbalanced loads are more affecting by common coupling to the source. So based on that non-linear and unbalanced load, we have gone for the simulation and we have given as an disturbance which we have created by a non-linear load. So the non-linear load we have given is an bridge rectifier, and for an unbalanced load, we have taken a three phases impedances are different. And this is a common figure which nowadays which has been going on into the virtual power plants also in the future. So where all the renewable and all the small scale which are being interconnected, and everything is an hybrid type of things where the power quality, voltage regulation, stability is also main concern for it. When we are going for the three-phase equivalent circuit of a shunt active power filter, we can see here it is a three-phase supply and the ZS is a source impedance, and from there parallelly we are connecting a shunt active filter so that we can compensate the disturbances which are created by the load on the source. If we are not connecting shunt active filter, we'll get, because of the load, non-linear load and unbalanced load, we'll get the disturbances to the source. So they are affecting the source harmonics are also produced. So based on the load current variations and harmonics. So that's how we have first gone for the shunt active power filter design. Next is we have gone for the four-leg converter model. In the four level converter model, so the converter topology, which is generally considered in the conventional, is a four-leg connected neutral bus system. The four-leg which is increased based on its number of states, like 2 power 3 to 2 power 4, based on its flexibility. If we take example of a multi-level or a matrix type of a converter, based on the number of levels we are increasing, for some applications, the total harmonic distortion will increase or total harmonic distortion will decrease. So depending upon that, our particular leg number of switches which are there in the leg is been varied. So this is a two-level four-leg PWM VSI technology which we have considered. So the basic level is a two-level, and the next is three-level and five-level also we have adopted. We have not gone for the high level. So we have tried for two-level, three-level, 5 and 9-level, but 9-level still we have not obtained the results. So I kept only for the two-level and not gone for the comparisons for the three-level also. So this is a VDC, and these are the switches per leg. We can see 2 switches are there. So 4 2s are total 8 switches we have considered here. And this is a equivalent load which we are giving to the to the load to the distribution system which we are connecting. So these are the switching states formulas and the output voltage which has been expressed in the mathematical equation. So here we have not used any mathematical modeling. Here we have used the SimPower systems. Based on the SimPower systems, the library tools have been considered. So here our main challenge is a controller which we are designing here. The controller is the one which we have designed. The controller is a predictive control method we have done. That is a model predictive method we can done. So the model predictive method can be done in two ways. Either we can go for a toolbox, or we can also take an example of in terms of an optimization technique. And from that we can go for the predictive analysis. So separate predictive model is been considered, and current reference generator, cost function is given, and 4-leg inverter is given with a feedback type of a system. So based on the feedback system, the total harmonic distortions are identified in terms of a current variation. Either we can take for voltage THD or we can take for current THD. We have taken for the current in terms of current, and we are checking the total harmonic distortion. So this is an DQ based current reference generator, which we have taken a block diagram, that is AB0, that we have used a PLLs for that, for additional phase shifting. So ABC to DQ0 and DQ0 to AB0 transformation has been done. So this is a inner block diagram of an transformation. And one of the advantages for doing a DQ0 is we can see that it makes into a linear, that is non-linear type of an analysis is difficult to analyze. So we are going for a non-linear to a linear, because again, if you want to go for a stability, we have to go for a Lipno type of a stability or something. So we have gone for a linear controller. We have made it into a linear controller, and then we have gone for the stability harmonical distortion testing. And then after that, we have gone for the three-phase conversion back. So this is a photovoltaic basic block diagram which we have considered converter. So the converter here we are using is inverter, not rectifier. From there we are going for the DC AC load. So this is an internal diagram of an practical PV. This is we have not designed we have selected a battery like NIMH or NICD. So the by default the battery backup is also available for it, where energy can be stored. So these are some of the characteristics of an PV cell. This is just an introduction. So this is our simulation with a predictive control scheme which we have used. And these are the results which we have proposed. So the first one is a phase to neutral source, and the second one is a load current, and third one is a load neutral current at the PCC point, and three-phase source current and compensating currents. After the fault is occurred, how we are compensating it, and the DC voltage converter. So we can see at the time of a 0.5, we have given an 0.5 to 0.6, we have given an fault is been occurred, as a fault is occurred by through circuit breaker. Based on that, it is been rectified. So these are the different three-phase source load currents, neutral line current compensating for a source voltage and also for the power factor, because the power factor is also very important in an AC when we are giving an unbalanced load and non-linear loads. So the total harmonic distortion we got as 29.988%. That is in terms of 0.29. As we know that it should be within less than 0.5 type of things. So it is within the satisfiable limit. So the predictive control scheme again subsystem is being shown, and these are some of the results related to the predictive control. So from here I could control that the predictive method is efficient for our particular closed loop type of a current loop of the simulation. So we can also go for a voltage and overall power consumption also. So here power quality we have not considered. We have taken only for the total harmonic distortion for the current. So we can extend it to the power quality in terms of an active and reactive power also. Based on that, we can go now, we can remove the nonlinear load as a bridge, and we can just connect to an electric vehicle, and based on a daily pattern of how the electric vehicle load is being given to the grid or the supply which is taken from the grid, we can do that analysis also. So these are some of the references which we have considered for our paper. Sir.
Thank you very much, Doctor, for your presentation. And here we go. I'd like to ask if anyone has a question for those presentations. Thank you, Doctor. We don't have a question for you.
Thank you, sir.
Thanks for your presentation.